So welcome back, everybody. And just a quick message about the recording from last week. So this is something which I haven't finalized yet. However, I do think that the PDF file plus the codes can help you in getting into the variational autoencoders. So in a way, we could title today's lecture as From Variational Autoencoders to Diffusion Models. And I wanted to display the differences, which means that I'm also actually going to repeat some of the mathematics behind variational autoencoders. And I also wanted to put this in context with Boltzmann machines so that you can see the differences between the methods. Now, diffusion models are extremely popular, and they are normally those which are used compared to variational autoencoders. But I will try to, in the slides here, to give you a little bit of the pros and cons of the different methods. The other thing which I wanted to go through a little bit more in detail is the mathematics behind these models and what is actually implemented in these different models and how you'd actually implement it. And we are going to continue with this topic next week as well. And probably we will also, towards the end of the lecture today, we'll try to run some codes where we also illustrate a little bit the difference between variational autoencoders and diffusion models. So diffusion models are extremely popular and are some of the methods which are really widely used into image generation, for example. Okay, so you can see now from the slides here, I also put in some of the codes in the PDF, but the way I'm structuring the lectures now is that the Jupyter Notebook becomes more a companion to the PDF, in the sense that if you look at the PDF, I mean, having codes in the PDF doesn't make much sense. So that's why when in the emails which I've been sending lately, is that I try to say that look at both the PDF and the Jupyter Notebook. Okay, so what I wanted to do then is simply to remind ourselves a little bit about variational autoencoders, but perhaps step a little bit back and even remind ourselves a little bit about the Boltzmann machines. So the first 15-20 minutes is a kind of a repetition of the Boltzmann machine plus VAEs, the variational autoencoders. So let's try to, let me just go out of the file here, and then we switch to the whiteboard. So what happened? What happened here? There we are. Oops. Okay. And we have that one. So now you should be able to see the whiteboard. Hopefully, there we are. There's a bit slow connection today. So if we look at what we have done till last week, so we are going to entitle this From Variational Autoencoders to Diffusion Models. So there will be some derivations again of things which we saw in the slides from last week as well. So if we look at what we are doing now, we have a domain of stochastic events. So with different stochastic variables, which we assume to be independent and identically distributed. That's an assumption we are making on the data set. So these X of i's are assumed to be independent and identically distributed. And we are then assuming that there is a probability distribution. So this is the quantity we want. And the generative methods actually give us a model for these. So we have X of I, which is drawn from this sample of stochastic event. And then we have multiplied with P X of I, which are the individual probabilities. So hopefully you see the distinction again between uppercase letters and lowercase letters. Then what we typically do now is that we have some kind of latent space. In Boltzmann machines, we call this a hidden space. So the latent hidden space has some explicit degrees of freedom. And the nice thing with the variational autoencoders is that these latent degrees of freedom in a way represent some kind of effective degrees of freedom. So we have a latent space. And if we go back to Boltzmann machines, we call this a hidden space. So we got additional degrees of freedom, which we could use in the optimization process. And this was then given by a set of hidden variables. And we will keep this label H for the hidden or latent space. And then this is given by H of I, which then belongs to a set H. So that means that we have H, which is then a new set of stochastic variables, which also have their own distribution. And I just put M minus 1 here just to distinguish. And what we had then, so this is just a reminder of what we've been discussing in the last weeks. So we have a probability distribution which now depends on some parameters theta. So these are the parameters which we want to optimize with respect to. And this contains some function which we call xf, and is a function of these variables. And then we had a normalization constant, which in the case of Boltzmann machines plays the same role as a partition function in statistical physics. But you can think of that as just as a normalization constant. So if we are dealing with discrete variables, which is normally the case, that's the most common case, then this is simply the sum over this xi and hj divided by z of theta. So that's a normalization constant, and this is a quantity which in the case of a Boltzmann machine actually causes problems for us in the optimization part. So I also wanted to bring this up because I wanted to say something about the so-called Kullback-Leibler divergence, which is a quantity which we encounter again in variational autoencoders and also in connection with diffusion models, and basically all these generative methods. So the other quantities which we have been looking at are the so-called marginal distributions. Let me just quickly remind you of these quantities because we are going to see them again and again. And we are going to play with these probability distributions and Bayes' theorem when we are setting up variational autoencoders and diffusion models. So what we have then is a probability distribution, which now depends only on the x's. And that means that we are summing away all the hidden variables. And at the end, whether we do variational autoencoders or we do diffusion models or we do Boltzmann machines, we're actually summing away these degrees of freedom. But we also, in the calculations, we're also going to need a marginal probability, which now depends only on the hidden variables. So I'm just bringing this up to remind you quickly of some of the quantities which you will see again and again in the derivations today, and divided with C of t. And then the optimization part, and this is something which we do irrespective of method. So we will actually, in the optimization, we are going to maximize with respect to a set of variables theta. So theta hat are the optimal values of log of t of x of theta. So this is the quantity to which we want to calculate the derivative of. And when we did Boltzmann machines, we had a difference between the two terms. And this difference is normally called a contrastive divergence. And you can also derive that from something which is called the Kullback-Leibler divergence, which we are going to set up today and discuss a little bit more. There is also an additional set of Jupyter notebooks where I actually elaborate on the Kullback-Leibler divergence and why this is a quantity of interest. And it's a quantity of interest also because we know that it's always larger or equal to 0. It's a convex function. And what we end up with when we have this optimization problem, the basic problem is actually this one, and we have log of P of X of theta. So for Boltzmann machines, what we ended up with, so I'm just going to set up the equation. So for the restricted Boltzmann machines, Bm, what we ended up with is that this quantity is given by the following equation. And then we're going to derive the corresponding one for variational autoencoders and for diffusion models. So this is given by the derivative with respect to a sum over the data which we have. So this is a log of f. So there is no normalization factor involved here. And we have summed away the hidden layer. So this quantity is something which you will also see mentioned as data. So this is something which then uses the data we have. And it does depend on a model which you have, but it uses explicitly the data. Then there is another term which enters here, which is given by the expectation value. And now we are picking x of I from this domain X, and we are using the probability distribution which we have. So this is something which then depends on the probability distribution, and this reconstructed probability distribution for Boltzmann machines depends on what's normally called a Gibbs sampling. And we discussed that 2 weeks ago. And this is normally often called the expectation part, because we reconstruct a probability distribution using a sampling scheme like Metropolis sampling or Gibbs sampling, which is a favorite one. And that is a way where we reconstruct the probability distribution. So what we ended up with then is then the expectation value of this quantity here. So there is a delta theta of log of f of x of I of theta. And you will often see that this has a subscript like model or just expectation value or reconstructed data. So this is the quantity which is called a contrastive divergence. And I just wanted to say quickly why these kind of words come up, because you have the contrast between two terms. So one term which depends on the data itself, which you have here. It's still model dependent, but this part here is actually a reconstructed model, or just slash reconstruct. And it's a reconstructed probability, because we are calculating these x of i's are now given by this probability which we want to define, x of I as a function of theta. And that term which you see there is actually the result of a Gibbs sampling procedure. Now, there is something which this quantity is equivalent with. So this is normally equivalent, this term which you see equivalent with what is called a Kullback-Leibler minimization. And I just wanted to say a little bit more about that, because this is often just shortened to KL. And the way you will see that is in terms of this expression, and we are going to use that later today. So KL, and it's often written with a probability. So this is a probability which now depends on the data set which you have. It doesn't need to be that. You can actually use this to compare probabilities. And another model probability, which we just call P theta here. So what this is given as is the following. There is a sum over all the stochastic events. And now I'm skipping this subscript I, so just write X, just to simplify life a little bit. And then there is a probability, P data of X, and log of P data of X divided by this quantity P theta of X. And you can see that this is equal to that term which we had earlier. So there is a sum here. If we now just write it out, so what you would get then is a term which goes like X, and then we have a P data. Sorry, not that one. Of log of P data of X minus, and then we have the probability distribution of X of P data. So we generate the points according to this term P data, but then it has now the log of P theta of X. And you can view this one, this last term here, as an expectation value. So we are going to reconstruct this P theta here by some Gibbs sampling, whereas here you can assume that this is just the data which enters. So this is the comparison with the terms which we had here. When you then take the derivatives, obviously, you take the derivative with respect to theta, and you see that in this specific case here, you end up by taking the derivative of this term and also the derivative of this term. So if you look at this Kullback-Leibler divergence, this is the function which actually corresponds to what we have here, except for the gradient term. Now, this term has some interesting properties. The divergence here was called the Kullback-Leibler divergence. And I just wanted to show you by using the Jupyter notebook. So the quantity here, let me just phrase that quickly. So this dk of L, and we will see that now through the Jupyter notebook of some probability P and Q is always larger or equal than 0. And you have an equality here if the probability you want to produce, because we want to produce a probability P theta. We assume that P data is something which we know. And then if the probability we want to reproduce is actually close or as close as possible to the real probability, the one which we think describes the data, then this quantity is equal to 0. So P equal to Q. You will also see that it's not symmetric. You can make a symmetric variant of it. And then it's called, and this is not a relative of mine, it's called the Jensen divergence, which we will encounter when we are going to look at the GANs a little bit later. So it's not symmetric, and you will quickly see that when you look at the equations, and I will show you some examples which you can play around in the Jupyter notebook. And so that means that the dk of L of P and Q is not the same as dkl of Q and P. And in the examples which I have online in the Jupyter notebook, you will actually see that when you play around with it. Then the other thing is that the dk of L, if you want to put some words to it, what it does, it penalizes, and you will see that now when it penalizes regions where P is larger than 0, but Q close to 0. So this is actually a feature which is quite important. Now, it's non-negative, and that is something you can see from the log which you have here, because the log itself, the log of this expectation value which you have, is actually, if you take the minus log, which is what you will have in here, this is a non-negative function, and we know that the negative log is a convex function. So that is a very important property. Now, one of the things I just wanted to show you is just some simple examples through the Jupyter notebook, and let's just do that. Somehow my laptop is very slow today. I don't know why. Maybe I'm running too many jobs here. But let's bring up the Jupyter Notebook. So there is an additional Jupyter Notebook in the lecture notes today, which I just call contrastive divergence. So one of the things I just wanted to say a little bit about, if you look at the Boltzmann machine, so what we put up now applies to the way we calculate the optimal parameters for a Boltzmann machine. When we do variational autoencoders, we will have a slightly different expression at the end, but we will use this Kullback-Leibler divergence. And that's why I just wanted to say something about it. So what you typically will see is if I just split this up in two terms, so you will have the definition here where you have the data. This is the same which I put on the whiteboard. And the first term is something which you can evaluate directly. So that does not depend on the parameters theta. But then you have a second term here, which depends on the parameter theta. So when you maximize this L theta, that is the optimization problem which you typically have in a Boltzmann machine. So these two terms are the two terms which you're trying to optimize. So as I said, it's non-negative, and you can quickly see that since the minus log is a convex function, this is a feature which applies to the divergence, or it's normally called the Kullback-Leibler divergence. And what I've done here in these calculations, I just wanted to show you not a Bernoulli set, but the perhaps easier probability distribution. So I'm saying now that P, so I have two Gaussians. And when I have two Gaussians and I take the ratio of them, then this ends up being an analytical expression. So this is a Gaussian which is centered around mu1 with variance sigma 1. And then you have another distribution which goes like that. If you have a multivariant one, then you still have a nice analytical expression, but you need to evaluate traces and a determinant of the covariance matrices. So if you then have a variational autoencoder, so I'm actually bringing this up here. I don't know if you had time to look at the slides from last week, but when I'm dealing with variational autoencoders, I'm actually using this Kullback-Leibler divergence. And one of the terms which I need to optimize simplifies because the probability distribution which I'm going to use for the latent space is actually given by a normal distribution, which means mean equal to 0 and variance equal to 1. So the variational autoencoders and diffusions models are very powerful, but in order to be able to compute, you have to make a model. So it's we can't escape that. And the Gaussian distribution is the most used model for this latent degrees of freedom. And I just put this up here so you have access to this notebook. If you just go to week 14 and look up the Jupyter notebooks, which are there. And for the in the variational autoencoder context, actually this Kullback-Leibler divergence, which appears in the equation to optimize, simplifies. And that makes the mathematics and the computations actually much, much easier. And what I did here was actually to compare two Gaussians. So if we look at that, and so I have just a ratio between two Gaussians here, and you can now see typically the interesting thing here is the effect of the variance ratio. So if you have exactly the same variances for the two, then you see that the Kullback-Leibler divergence is equal to 0. And you see also here the asymmetry. So these are the two types of equations which you could start with. And you see here now that they match perfectly, and that's where the divergence is 0. The function is convex, so that means that it's always larger or equal than 0. So it's a very nice feature to actually look at when you're comparing probabilities. And you will see that this is a measure which is used in many, many machine learning calculations. Now, I'm not going to go through everything here, but you can actually take a look at these codes here. The thing which is nice, and I just wanted to say that a little bit at the end here, There is also an application. I actually use this more in connection with Boltzmann machines because there it's very easy to set it up. And let me see if I put this up here or I forgot to do that. No, I have it in another place. So then I can just state it by words here. Let me just find the note. Okay, let's just wait till I find the notes again. But what I want to do now is to go back a little bit to the whiteboard here, and we are going now to switch over to the variational autoencoders. So we set up the equations for those, and then based on that, we are going to then take the next step, which is to introduce a diffusion model. So let's just bring back what we had in the slides from last week, and then link it again with the Kullback-Leibler divergence and the quantities which we set up for Boltzmann machines and see how they differ. And then when we have reminded ourselves about that, the next step is to look at diffusion models. So variational autoencoders. Let me now just simplify things. So these x's, I just replace them with xi's with x, and hj is then replaced by h. Also, in order to simplify the notation x and theta, the way I write the probability, I'm going to write the probability with respect to parameter theta like this. This is a target which we want to have. And we know, if we now use the product rule from statistics, we know that this p theta of x, that can actually be written out as the probability of finding x and h divided by what is called the conditional probability of getting h given a value of x. And we know also that these probabilities, if we now look at this p theta of x, if we now look at continuous variables, just for the sake of simplicity, you can easily replace that one with a discrete probability distribution. So this is given by an integral over theta over x and h. And that means that if I use the product rule, I can actually rewrite this in the following way. So I can rewrite this as a function over dh, an integral of p theta, and the conditional probability multiplied with the probability p theta of h. So we are going to make models for this in order to be able to train. The quantity which we want, the final quantity, is this one. This is the one we want to obtain. So just to quickly remind you of some of the things which we had last week. So let's now just look at the basic structure of a variational autoencoder. So you can think of a big blob here where we have the data which we are feeding in. So that's a given data set. It could be a set of images which we want to train a probability to reproduce. Now, there is a function now which transfers from the space x to the space h. And that's why it's called an encoder. So that means that we need to have a probability distribution, which is called Q of phi. So this introduces another parameter, which is not included in the final probability. And typically this function here, so this is h given x. And this becomes what we would call the encoder part. That encodes information from the data set and then transfers that one to a latent space. And it's often actually in the, if you look into the codes which we have for week 14, you will see that there is an example where you run a variational autoencoders where you can actually print out the latent space and see how that looks like. And hopefully, what you obviously hope is that the latent space can convey some specific information about the system which you have. Then what you will have in here is the so-called latent space up here. And there we have a probability distribution, which in the theory for autoencoders is normally approximated with a normal distribution. So that means a Gaussian with the mean equal to 0 and variance equal to. But you need to have a model. You can obviously change that one. And then this is used to transfer back again. So you have a parameter theta, and then you have x given h. And this part which you see here is the part which we call the decoder. So that decodes information like we had with an autoencoder. And then it transfers the information over here. And what we get then at the very end is p theta of x. And in here, we are going to produce new images. For instance, x tilde would be the new image. And this x tilde is produced from this distribution which we have here, where you now can use the x's, the original data set. Okay? So what I want to do now is simply to set up the derivation again of the variational autoencoder. Keep in mind now that this is the quantity we want to optimize, this one, in terms of these parameters theta, but we also have a set of parameters here which we need to define. And if we go back to what we had, essentially what we are going to do is this problem here. This is unchanged. And that means again that when we have put up log of p of x, we are going to have a set of equations. And from these equations, we are going to calculate the gradients, period. Okay? So it's basically the same recipe, except that we get slightly different equations. So for Boltzmann machines, we had this contrastive divergence between the two terms. Here we're going to get a slightly different equation. So let us just go through them. And if we now look at the derivation of the VAE equations, so we want the log of, of p of x of theta and its gradient. So let's do the log first. So if we do the log, what we are going to use as a small intermediate trick is that this q of phi, which is a distribution which we haven't defined. So this is q of phi. So it's a set of variable phi, which we need also to include in the optimization. And h given x. So this is a conditional probability. All the probabilities are obviously normalized. So this is equal to 1. So what I'm going to do then, when I take log of p theta, so this is a quantity which we are going to derive now. This is obviously equal to log of p theta of x, but nobody hinders me to multiply it with 1. And I have defined 1 as a term which you see here. So I have an integral over q phi x of h multiplied with d of h. That's equal to 1. Now, this is something, since p theta of x does not depend on h here directly, I can obviously rewrite this as q of phi of h of x. So this is a probability of log of p of theta of x of dh. Now, this is nothing but an expectation value because I have a probability times a function. So I can actually rewrite this as an expectation value where I now compute these h's according to this probability q of phi. This is just a notation. It simply means that h is drawn from this specific probability. Obviously, to run these calculations, you need to have a model for it. And I'm coming back to what this model looks like for the q's. And this is the same as log of p theta of x. So what we are going to do now is simply to rewrite this term as a function of if we look back here, we are now going to introduce this notation which we have here. So because then we link with the h's. So let's continue with this kind of derivations. So what we get then is the following. We are going to have that this expectation value is equal to the expectation value of h drawn from Q of phi. And now I'm using the product rule. And the expectation value of log of p theta of x and h divided by p theta of h given x. So this is just a product rule, which I'm just inserting here. So if we go back, let me just show you that. We had defined this expression here. So this is the standard product rule from statistics. So I'm just using that one. So I replace that one with the product rule. And this is what you see in the equation here. So that's the product rule. Then I can now repeat the trick again because I want to rewrite this in terms of the Kullback-Leibler divergence, because when I choose a specific model for some of these probabilities, that will actually simplify the calculations. So what I'm going to introduce again is magic number 1. And 1 in this case is actually given by Q of phi of h divided by Q of phi of h of x. Okay. So that gives me the following term. So I have E expectation value with h drawn from this probability, which we haven't said anything about yet. And then we have log, and then we have the log of p of x of h, so of theta. And then this is multiplied with q of phi of h of x. And then we have p of theta of h given x, and multiplied with q of phi of h given x. Okay, so this is something which we then are going to rewrite in terms of one term which contains the Kullback-Leibler divergence. So you can now see that when we have the logs here, we can actually rewrite this in terms of 2 or more terms. So let me just write that one down. So if I do that, what I'm going to get is one term Q of phi, and then I have my log of p of x given h of theta divided by q of phi of h given x plus a new term. These are expectation values of h of q of phi, and then I have log, and then I have q of phi of h given x, and then divided by p of theta of h given x. Now the last term is one which is a Kullback-Leibler divergence lookalike. So, and we're actually going to replace that one, and we know that that one is larger or equal than 0. So that means that this term which you see here is nothing but this Kullback-Leibler term, where we have a q of phi of h given x, and then I have this double bar of p of theta of h given x. And we know that this term is always larger or equal than 0. So let me just put that in parentheses here. So it means that I can actually rewrite this log term And keep in mind now that I actually have to take the derivatives of these terms afterwards. Now, depending on the function Q of phi, which you opt for, that can actually simplify this DKL in the calculations of it. But what we end up with is the following expression. Let me just put that one up here. So we get E expectation value of H of Q of phi. And then I have my expectation value of this log of P theta of X of H. And we're going to massage that one further a little bit. So we have a Q of phi of H of X. And then plus, and I'm going to put some space in here, we have the Kullback-Leibler divergence. And I just write this as a Q of phi of H given X. And then P of theta of H given, of H given X. Now, this intermediate term, which you see here, the first term, has a name in the literature. And this is the term which becomes important in the optimization. So this is ELBO. It's actually called evidence lower bound. Or lower variational bound. It's actually a variational bound, which it becomes important because these quantities are also larger and equal than 0. So the Kullback-Leibler divergence is something which we know how to handle. And the next term which we need to deal with is actually this one. And this one can actually be changed. So we can manipulate further this term which you see here. So this term, if we now remind ourselves that P of theta of X of H is actually given by P of theta of X H times P of theta of H, then we know that if we now integrate away H, then we are left with a probability which we are interested in. So this is given by a D of H of P theta of X given H and P theta as a function of H. So I can now actually go back to the equation which we have here, and I can replace this P of theta with this function here. So that gives a slightly different term, which is going to give me another Kullback-Leibler divergence and a final term, which is the one which we need to evaluate properly when we run the calculations. So if I now include this expression which we have here, let me just bring it up again. So what we're going to do now is to plug this one in, this expression here. And that's going to give us two terms. And one of them is going to, again, be a Kullback-Leibler type divergence. And depending on the type of model which we choose, actually that term can be calculated as you saw in the Jupyter notebook here. Now, just to quickly remind you before we take a small break, if you look back at all these steps here, it's important to just keep this image clear. Because if you look at this image here, then you have the basic steps which will be included in the setup of the variational autoencoder. So we will need, and we will see that after the break, we will need a model for Q of phi. We need a model for P of theta. And when we have that, then we can obviously calculate the expectation values which we put up here. So that means this expectation value. When we have a model for P of theta here, then we can actually try to evaluate this function. And then since we have a model for this one, we can actually evaluate that one as well. Okay, so let's slowly go through the next step, where we now write out this term, the first term here. The Kullback-Leibler divergence is now defined, and the quantity which becomes important for the optimization when we are going to calculate the gradients, because this is just the log of the probability distribution. So what we need then is a gradient with respect to the parameters theta and the parameters phi. Normally this Q of phi is fixed, so that leads to no optimization there. So after the break, we're going to put up the final expression. And when we link this with diffusion models, the link which you will see then with that is that a diffusion model can be seen as a set of connected latent spaces. So with a variational autoencoder, in a certain sense, is actually a variational diffusion model with only one step here. Okay, let's take a small break, okay? Okay, so before the break, we actually put up this equation, this elbow, which is called evidence lower bound. It's a variational term. It contains a equation which we are going to rewrite. We have a Kullback-Leibler divergence here. And then at the same time, we are now going to reintroduce the product rule, which allows us then to find an expression for this P of theta as a function of x and h. So let's rewrite this in terms of this term, which we have here. So let's redo that. So then what we will get is a function which looks like as an expectation value of h drawn from Q of phi. And then we have a log of P of theta of x given h multiplied with P of theta of h divided by Q of phi of h given x. So if you look at that term in particular, so the not the final term, so I should actually put an equality sign to this term here. So this is the term we are looking at now, not the Kullback-Leibler term, which we have there. So this is something which we then can rewrite as an expectation value with respect to Q of phi. And then we have a log of P theta of x given h plus a term which is actually given by Q of phi of log of P theta of h and divided by Q of phi of h given x. So the first term is something which is normally called the reconstruction term. And we can rewrite the last term if we now interchange the numerator and the denominator, we get a minus sign. And then that is something which we can rewrite as a Kullback-Leibler divergence. So we will have the first term, which is h Q of phi, which is called a reconstruction term of P theta. And then I have x given h, but then minus, and then we have the Kullback-Leibler term, which is called a prior matching term, because P of theta plays the role of a prior function in Bayes' theorem, and we need to set up a model for this P of theta. So this is the Kullback-Leibler divergence of Q of phi of h of x, h given x, and then with respect to P theta of h. Now, when we run these calculations, we're actually going to make models for when we calculate this Kullback-Leibler divergence. If you look back into this Jupyter notebook, which we have, we're actually going to approximate this with two Gaussians. So the typical term now is that since we have this Q of phi of hx, this is treated as an encoder. So that's the encoder part, as an encoder. And the standard approach, which is used throughout the literature, is that this Q of phi of h given x is proportional to a normal distribution where we have a variable h, and then we have a mu of phi for x, and then we have a sigma, a variance with respect to the phi. So this is normally a multivariate Gaussian. So in the Jupyter notebooks, which we have for this week and also last week, there are examples on how we treat that. Then we need also a model for this prior, for the latent space. So typically this P of theta of h is assumed to be independent of the angle theta. So this is simply replaced of a function P of h, which is then given by a normal distribution with respect to h, with 0 mean and 1 as variance. That's a standard normal distribution. So what we're doing then is actually to make models. So when you have these two, if you go back to that Jupyter notebook where we looked at the Kullback-Leibler divergence, that means that this expression which you have for the Kullback-Leibler divergence is actually an expression, this term here, which is just given in terms of simple functions. And it's easy to evaluate. And that is one important thing. So the quantity which we need to evaluate then is actually this reconstruction term and the other Kullback-Leibler divergence. And you will see in the codes the 3 different terms which you get when you then do the optimization. So this is roughly what we end up doing. And it means that this term which we have here, which is an expectation value, this one, is then an expectation value where we draw these numbers according to a multivariate Gaussian distribution. And it means that we are calculating this as a standard expectation value with Monte Carlo sampling. So when we look at diffusion models, on the other hand, this is the step which I wanted to bring in. So I wanted to just set up the equations for variational autoencoders. What we are going to be inspired by is actually the physical process of diffusion. And when you think of diffusion, that is intimately linked with Markov chain. So let's take a quick look at the diffusion and Markov chain. So this is our next step. And I just wanted to remind you that as a kind of intermediate step. So diffusion models and Markov chains. And when you see the basics of mathematics, of the basics of diffusion and Markov chains, you can see how we are going to introduce this diffusion models as a set of a sequence of latent spaces which are connected. So that means that we also then need to have some functions which connect different latent spaces. And again, what you're going to see then as a kind of encoder part is that these are also going to be given by Gaussians. Okay, so let me quickly remind you of that. We know that if we have a probability, P of I, of being in a state I at a time t, if we are using time, then this is given. So this is just a definition of a Markov chain. Then there is a transition probability, which now tells you the probability of moving from a state j. So you assume that the system is in a state j at a time t prime. So the next probability depends only on the previous one. And this quantity which you have here is normally called a transition probability. It can be time dependent if you want to use time. You don't need to think of time, but time is very natural as a unit here. A transition, this is a transition probability, and it can be time dependent or not. The important thing, if we now think of these as vectors and matrices, is that P of t as a vector contains now you could think of each one of them as a state the system could be in. So 0 could be position 0, P1 of t. So this is a vector. And then you have something like m minus 1 elements of that vector. And obviously, if I sum over all the individuals P of I of t, that has to be normalized to 1, since these are probabilities. Okay? So that's one thing. And then T is what we call a stochastic matrix. I guess many of you are familiar with that. A stochastic matrix, in case we have a finite dimensional system, a stochastic matrix is so defined that if we sum over the columns or the rows, this is normalized to 1. Also, the largest eigenvalue, lambda max of T, is equal to 1. So that's the absolute value. Now, what we know then is that if I repeat this many times, so we repeat many times, then what we typically have is that the P at the step Tn is then equal to us having applied this matrix n times on an initial. So now I'm writing this as a matrix times a vector. And that means I should put a vector sign here, and then we could start at the sum T0 here. So this is a typical way by which you would set it up. And you know that when we take the limit, in the limit where Tn goes to infinity, what we have then is that the probabilities become independent of time. So we have reached the most likely state. That most likely state is the state which corresponds to the eigenvectors of this matrix with eigenvalue 1. That is normally called the most likely state, or the stationary state, or the equilibrium state. And then what you would have is that this is given by the matrix T times a vector P. And then you see that the eigenvalues are equal to 1 for that specific state. And this is something you can show when you look at the master equations. I'm not going through all these details. But now you may ask, where do the diffusion models come in here? So the way you can think of this, if you now look at what we had with variational autoencoders, is that in the variational autoencoders, we just had one latent space. So we had the decoder part in here. We move into the latent space, which hopefully gives us some effective representation of the degrees of freedom, a reduced set of degrees of freedom. And then we can reconstruct things through the decoder, and through the decoder here and the relevant equations, we can then reconstruct the final probability, which in our case is then given via the standard product rule as we wrote here. So this is the final function we want. And in the optimization, the part which we're interested in is actually this one. Here we have a model. We said we had a normal distribution, and we also have a multivariate Gaussian for that. This is the variational autoencoder. So if we now look at the diffusion models, the way we can think of them and this process of diffusion is in the following way. And this is normally called a variational diffusion model, because we are going to get equations which are similar, which have a variational bound. So this elbow, this evidence lower bound, is going to pop up again. And we are also going to encounter different types of the Kullback-Leibler divergence. So the way you can think of this now is, suppose now we take away time. But suppose this is the original data, x0. This is the one you now want to reproduce. So what we want is an x tilde. X0 is the input data. The data, this could be a set of images which are input into the system. And this is going to be something we want to extract from the probability which we have trained. So this is the equation which we are going to derive the probability of. So x0 is your input data. And then what we're going to have now is a model where we have a latent space, H1. And here we are going to have a function which connects this one. So this is a variational autoencoder lookalike. So we're going to have a Q of H1 x0. So we're going to set up a model for that. But now we are getting more ambitious, so we are going to have more latent spaces. So we can define as many as we want here, and then the calculations get heavier and heavier. So we can now have a Q of H2 given H1, and this can continue now up to some H of T minus 1, and the final one, which I just call H of T. So these are all latent spaces. That means that when we connect them, and you see now that the Qs have to be, in order to be able to run calculations, you would actually need to have a model for it. And again, this model is going to be a multivariate Gaussian. Okay? So we would then have all these new ones, and at the final one would be a Q of H of T minus 1 and H of T. So what we are going to get is a series of latent spaces. The next thing, when we have this, and what you're going to see is that this is going to represent a kind of denoising of the image. So the image starts by being sharp, and then it gets more and more blurred, but then we reconstruct it. So what we're going to have next is actually a probability which links these two. So now we have a probability of H of T minus 1 given H of T. So if you think back to the variational autoencoder, in the variational autoencoder, what we had was just a P of X given H, which we used in the reconstruction. And that was the term which we optimized by the expectation value. In addition, we had this Kullback-Leibler divergences. So that means that when we now do this, we need to make new transformations and all the way back to the final one. So we're going to have a P of theta, which links H1 with H2. And finally, we have a new P of theta, which links X0 with H1. So think of this as a chain of latent spaces. And each one makes some transformations on the images, if it's images we are interested in. So we are not limited to images, obviously, but I'm using images because it's a very easy thing to think of. And you probably see now ad nauseam, this MNIST data being used again in all the examples. And you may think that I don't know of any other data set than just the MNIST. But as I said, I'm using that because it's something which you encounter in basically all textbooks. Okay, so what I want to do now is to shift to the to slides, and then I wanted to try to systematize things. So hopefully that can allow you to see the wood for the trees between these different models. So let's try to see what enters these various calculations. So I'm going to use the slides for the rest of the lecture, and these are the slides for this week. And if we get time, we will start looking at the codes as well, unless the codes we're not going to finish in time. So as I said, I wanted to bring up this link with the Boltzmann machines and variational autoencoders, and hopefully you see the difference between the way we optimize. So now we are going to look at a little bit the definitions here. And a lot of this material is actually taken from the original article by Kingma. Kingma is the same person who developed Adams. So Adams, this way to update the learning rate, has more than 200,000 citations. And Kingma's article on autoencoders has some 60, 70,000. As I said, a good scientific paper has roughly 100 citations. So it's pretty impressive. But there are also some, if you look at this article by Calvin Luo, there's actually a pretty good discussion of the mathematics, and same with this article by Kingman. So there are some things now which we are going to encounter, we have encountered in this course. So often my main focus has been on these three methods. But if we get time, we will also say something about normalizing flows, if we get time towards the end of the semester. And we also have a session on GANs, which is a way to implicitly derive the generative method. So the architecture here, as we have seen, the autoencoders, the variational autoencoder. We have a model for the latent space, which is a prior. So I took away the subscript theta, and we just went through that in the, so this is just something which we are going to look at when we set up the codes. So we have a reconstruction term, and this is often called a regularization term. And these are the equations which we looked at on the whiteboard. And then obviously you need the gradient of this function. And since this KL is large equal than 0, then this elbow is a lower bound on the log evidence. So maximizing the elbow simultaneously maximizes the reconstruction quality and minimizes the gap to the true posterior. So the elbow then is tight only when these two guys here actually are close to each other. So this is taken as a multivariate Gaussian, but that's the only time when they are actually close, when they are close actually. So to backpropagate, this is just a reminder a little bit of what we have in the slides from last week. There is a sampling node. You would typically write this H in terms of the mean value plus the variance, and then the dot product with a noise, an epsilon. And the gradient is then typically estimated for this quantity here in terms of this specific function where you have phi. This is the transformation from the data to the encoder part. And that part, which we are normally using when we now look at the KL divergence, we normally, if we're Gaussian, we actually have a nice analytical expression for the KL divergence. So this is one of the things which you could say gives less flexibility, but it gives more efficient ways of doing things. But you could obviously replace that probability with other probabilities. So if you look at the variational autoencoders and you want to look at strengths and limits, so you actually have a nice probabilistic framework. You can deal with continuous latent spaces. You have efficient ways of passing to the encoder and from the encoder to decoder. Stable training. The elbow can actually be easily evaluated. You often get blurry samples. Gaussian decoder averages over modes. Posterior collapse, powerful decoder ignores H. You have a Gaussian prior may not fit complex data. So this is one of the, how to say, the criticism of it. The elbow gap, like this log P of X, is never exactly recovered. And there's a limited expressiveness of different types of approximations. So if we now look at the diffusion models, so what you're typically going to do then, so we want this P of X from the first latent space to the final latent space. That's what we want. And that means that we will have some, and now we are just using the product rule for probabilities. So this is the probability, the prior for the final latent space. You have the transition from H1 to X, and then all the other ones. And then we need these guys. So that means that we will have a Q of phi here from the first latent space to the final one, given X. And so if you go back to that figure, which we draw in a very schematic way, this is just setting up the mathematical expressions for the various terms. And these are just the products of these terms here. And then when we want to optimize, the log P of X, which we have, is now going to be given by these quantities here. So we actually get a probability distribution, this Q of phi, as we did with the variational autoencoders, where we now have this lovely chain of products. So if you were to do a variational autoencoder, you would just have one latent space. So then you would only have this one, and you would have that one. So if you take away the products here, you're actually back to the variational autoencoder. Okay? So each level actually adds a complication, a new reconstruction, or a new what we normally call a regularization term. So we normally call this a variational diffusion model. So it's a Markovian process because you actually have all this probability being multiplied with each other. So it looks like a standard Markovian process. And it's a full dimensional latent. So that's a constraint which you have. And the latent variable, the final one, lives in a data space, not a compressed bottleneck. You have a fixed Gaussian encoder. So that means that your Qs are given by a multivariable Gaussian. This is not trained. It is a fixed part, which has a kind of, which also contains a kind of noise. And we're coming back to that next week when we're going to look at the codes. And this alpha t here is chosen so that when t goes to the final time, the final one is actually given by just a normal distribution. So if you now look at the basic mathematics, so you would have all these kind of cumulative so-called noise levels. And by using this Markov structure, you have actually a closed form for these marginals at any time t, when you only have given x. So the closed form expression is actually given by this one, which is now a multivariable Gaussian. And you can then, when you start from that one, the Gaussian convolutional formula gives you, if you actually use the standard Gaussian formula, you can actually see that this is the case for the x's. And epsilon is then just a noise which is added to the system. So you typically have two common schedules, and one is to, this is actually taken from this paper here, and I may actually not say so much about that before we look at the codes. I can come back to that. So the forward posterior is then simply given by this multivariate Gaussians, and we have an explicit expression for these mean values in terms of the previous terms. So this is typically the target for the learn reverse process. And then when we have that one, we are going to put this back into the elbow equation. And then this is the term which we now are going to use in the reconstruction. And then we have this series of, we have this Kullback-Leibler divergence and the sum of all these kind of terms, which are normally called denoising and matching terms. So if we have just one of these terms, I mean the first term here, and we exclude all the other ones, then we will be back to the traditional autoencoder, variational autoencoder. So this term in the first derivation involves two random variables per step. That normally gives a pretty high variance. And that means that the condition on x0 at each step means simply that we would replace, if we now look at this term here, that term would then be replaced by the one which links a time t with a time t minus 1. And that reduces actually each KL term to an expectation over one random variable. And that substantially lowers the Monte Carlo variance. So you end up evaluating this type of Kullback-Leibler divergences, which actually have closed forms. So if we choose this probability here, the probability xt minus 1, when we're stepping back, given in terms of a Gaussian, then the Kullback-Leibler between two Gaussians with equal variance reduces to a squared mean difference. And you can further reparameterize this one using the formula which we showed previously. So there's a lot of kind of different tricks which I invite you to take a look at when you now want to understand a little bit deeper what the diffusion models, how they're actually implemented. So the typical training which you end up with is something which is given by this expression here, where T is then given by uniform distribution. So I'm going to skip some of these terms here. Again, I can skip that one. So I just invite you to take there's a PyTorch. I wanted to have a comparison. So this is the same thing which we have in the codes. So if you now look at both the variational autoencoders and the diffusion models, they both optimize a variational lower bound on this log P of x. So the latent levels is typically just 1 for a variational autoencoder. But here you can actually have hundreds or even more. And what you will see when you run the codes is actually that the code is going to be pretty slow. But it often gives a much better result than a variational autoencoder. So the encoder here is normally a learned Q of phi, whereas here you have fixed Gaussians. Here you also have the inference part, just a single forward part. Here the decoder is actually what you learn from that part. And then you've learned a denoiser, so which is a product of all these kind of probabilities. And then the sampling is actually given by a single decoder call in the variational autoencoder, whereas here you do this T times. And then the elbow terms, you actually have 2 terms only, which we saw from the equations, one the reconstruction term, and another term which is just a Kullback-Leibler term. Whereas here, in the case of a diffusion model, we actually have a sum over many such terms. So that obviously means that the training and evaluation becomes much more tricky. And similarly, we have a simple reparameterization here. This is a trick which we have in the slides and is discussed in the slides from last week. Whereas here we have a similar term, but this also includes some kind of noise term epsilon here, which is normally distributed. So if you want to make some kind of pros and cons of these methods, the variational autoencoders is fast, pretty compact. There's only one latent space. It's normally pretty stable with respect to the elbow training. It's closed form for the Gaussian encoder, which is also makes things very nice. But you can often get blurry images. And I see that this is actually, here we have a, nope, not that one. So there is always the risk of a posterior collapse. If I take the diffusion models, in that case, you can have a pretty sharp, high quality samples. It's normally stable. There is often not a collapse of the procedure. Theoretically grounded via elbow and score matching. However, it can be pretty slow. And there is no compact latent representation. It's actually high memory compute for large values of T. So the sampling here is actually done with 100 at least types of latent spaces. And clearly, when you run the codes, which we have online, you will see that things are going to be pretty slow. So when should you use it? I would typically say when you have structured compressed latent spaces for, let's say you're doing clustering, anomaly detections, real-time generation. Data has low intrinsic dimensionality relative to the observation space. So if you have One of the cases, if you have structured scientific data, that can be a case where a variational autoencoder can be useful, where you have often a simple relation between the original data and the latent space, if you have something like that. Also, if you, the thing which is nice with a variational autoencoder is that you can quantify the uncertainty, which is very important. If you use a diffusion model, this is typically the model which is now being used for images, for videos, audio. You need to do conditionally on complex high-dimensional signals, text to image, super resolution, etc. Training stability is more important than speed. And you have the compute budget. And you will see when you run the codes, which we have online, that they are pretty slow. And if you run on a CPU, you can just sit there and wait for a long, long time, even for the simpler endless data set which we have. So I was thinking of one thing. So we are a little bit, we're close to the hour, but it would take me a little bit more time to discuss the codes. So what I would like to suggest is that we stop here today. And then next week, we go back to the formalism and we link that with the codes which you have. And I'm going to try to speed up the code so that we can discuss the results in more detail. So for next time, take a look at the slides which we have here, which link with the Jupyter Notebook. And then we are going to look at how we can typically implement it and continue a discussion of the pros and cons of these methods. And so next week, we will also spend time on diffusion models. And if we get times, I will say something about GANs. The week thereafter, that Thursday is a public holiday in Norway. And so that means that the last time when we also will do a summary, I may say something about normalizing flows then, would be Thursday, May, and I think that's May 22nd or 23rd. No, wait. So 14th plus 7th, 21st. May 21st is our last lecture. But May 14 is a public holiday and it's Ascension Day. And then so next week, we will most likely spend most of the time on the codes for diffusion models and also introduce, if we get time, GANs as one of the other standard methods for generative learning. So I'm going to stop a little bit earlier. I hope you don't mind because I often go over time normally. And then we reserve next time for discussions of codes.